So here's how we use that information to simplify and speed up our interpreter. We're going to have a compiler that takes an exp and translates it into an equivalent form, but one that doesn't have any IDEs in it. So far we have exp produced by a parser. We're going to introduce a compile function that changes an exp to an expd, and an expd has numd, add-d, multd, all the same as exp has nume, add-d, multi, but instead of IDE, where there's a symbolic name, an expd is going to have an at-d, where there's a position name, position instead of a name. Appd is going to be the same as appb with a function and argument subexpression, but lam-e, again, we drop the name. In the case of a lambda, that means we just don't need the name, we only need the body. So when we apply a lambda, we will still need to add on to the environment, but we don't need to remember a name to use for that addition to the environment. Let's look at some examples of how compile should work. On the left-hand side here, the black boxes, those as usual correspond to parse of the concrete syntax inside of it. The orange boxes on the right correspond to a hypothetical parse that produces expds instead of exps. And what this example is showing is that when we compile 1 as created with nume1, then we should get 1 as created with numd1. And the same for our addition expressions. Addition just compiles to addition. But when we have a variable, and especially if it's a variable that's just all by itself, then we're going to do something different. We can't compile x to an orange box x because there are no x's in orange box. In fact, if we were to evaluate this expression, then what would happen at runtime is that we get a free identifier error. So we're going to have our compiler react to free identifiers like this by raising the error early before we even interpret the program. And we'll just be happy that we're getting earlier errors. Here's a case where we have an x, but it's not an error. It's not a free identifier. And so we want to compile this lambda to one that's similar. It should be the function that takes an argument and adds 1 to the argument. In xd, we represent it this way. It's a lambda with no argument name because we don't need any names, and then plus 1. And here we're using the at form, which is at-d and an xd, with the index 0, because 0, counting from 0, meaning the first thing in the environment. Because when this function is called, that's exactly where the x will be. It'll be the most recently thing added to the environment. Here's one more example. I've got a lambda y, lambda x plus xy. So it's the function that takes a y, takes another x, and then adds x to y. We compile that to a function that takes some argument and another argument, but we don't give the arguments names. And then we add the value at position 0 and the value at position 1. Position 0 corresponds to the x that's passed to the second lambda, whereas at 1 it's going to be, we can count lambdas just like we count y's, it's going to be the second thing there, or index 1.